Today, we have the pleasure of having Professor Guoqing Hu, who is going to talk about natural vector methods and artificial intelligence applications in bioinformation.
Thank you. It's my pleasure to be here to give a brief introduction of what we are doing. I joined the BIMSA over maybe a year ago. Yeah, that's I only studied this one only a year ago. Yeah, that's very interesting. That's today I can give a topic on this one. And let's see what we are doing. Now, basically, we try to see from mathematical point of view how to we study, analyze those bioinformation. That's our from mathematician. So we have that. We know that's bioinformation. We have the DNA, like here that's DNA or protein sequence. They call the format fast sequence. Basically, the idea is that the DNA for DNA example that's ACGT. All those are long, very, very long sequence, very long. Okay. For the COVID-19, you can think of that 30,000 those long. Okay, basically we try to, that's okay, convert those one, that's a sequence into some numerical point. That's our natural vector method. So once we get those, that's you can call this embedding or encoding those one, okay, using the natural vector. Then we can use this AI, combined with this AI. Machine learning user our neural network, like here in one of the paper we use that's random forest, XRP boosting, those kind of method. Then we, that's contraining those models. And finally, we do the prediction, predicting some maybe new sequence or maybe new functionality, anything, okay, after the training the model. So basically, that's the idea. That's how we, that's the general idea, the framework using our neural network, using our natural vector method. Okay, so that's okay, we from the sequence to some numerical floating point, then get the AI involved, training, and do the prediction. That's a general idea. Okay, so what's a natural vector method? That's Stephen Yau's, our team's key method. Okay, it's a tool like, okay, the natural vector basically that's a transform those DNA sequence into numerical form, like I said before. Okay, so for example, that's we have this one that's a sequence, for each, we call that a nucleotide. That's nucleotide, that's for DNA, that's ACGT. You can think, okay, it's each position, it's ACGT, that's correct form. And for protein, that's 20 characters. Okay, if you don't have the background for that one, you can just think of that's correct. Okay, then we can define something. From mathematical point of view, we can say because that's very long. So one way that we can define, okay, how many numbers count those nucleotides. Like, okay, this one, how many A appears in this long sequence, and how many C. So that's very natural, right? We define this one. So for this ACGT, so this count have the 4 dimensions. That's how many of A, how many of C, how many of G, T. Then we can get that, okay, what's the average position. Okay, you can think of that's a mean, right? That's A appears here, here, here. What's the average, the position? So that's, that's, if you think of, I try to capture those sequence, the characteristic of the features. So that's a very important, another 4, dimension, the features. Then we can define those jth order central moment of the position. Then we can define, okay, that's a jth order. If you think j is a 2, here that's okay, gets a 2. Then, for example, that's okay, we studied this 4 dimension 4 mean, and then plus this second order, another 4, then we get the 12 dimension natural vector. Okay, very clear. If we want to study more, that's a high order. Each time you give a high order, then you plus another 4 dimension. So you can extend this one to a very, very long dimension. But there are some drawbacks. Okay, we can see what's a drawback. The drawback is here. That's as long as you have the JS dimension high order, that goes to the 0 very fast. Okay, so we have some other improvements. Now, one of the improvements is a symmetric covariance natural vector. That's basically, you can think of, okay, in the original one, we only studied this single character, ACGT. Even for the high order, that's still, the single. But then you can think of, because you have a sequence, the position, the relationship, A followed by a C, Y are not T, right? That's important. So we want to study the relationship. Then we introduce the covariance. That's basically, okay, with a K and L, like AC, what's a relation? Then we can define this formula. Now, in this formula here, we only consider here, we call the symmetric, because in this formula, if you define, that's a symmetric. So like, okay, if the two, merge, like AC, GT, that's a two character. The combination of this one, if the plus the symmetric, then you can only have the 18 dimension vector. So that's a 18 dimension vector. We plus this one, plus all the others, we have this added, this one. But there's also some drawbacks for this one. You cannot extend it to, high order. So then we introduce this one, a symmetric covariance. That's what I studied, last year. When I come to this one, we, propose this asymmetric. The asymmetric, the key point is that, okay, we captured this one. That's a directional information. Like this one, the symmetric, okay, AC versus the CA, they consider the same thing. But in the sequence, okay, AC with the CA, it's different, right? It's a from Bioinformation, those logical, you must think of that's different. So that's why we introduce the asymmetric covariance. And we define, okay, there's some position, as you can see, added. But the indication function, later we'll give an example how to calculate this one. But the formula is this one. So for the asymmetric, then we, extended, like all the first 8 is the same thing. But here we have the, you can think of that's a tumor, like 14, that's 4, F tumor, that would be 16 altogether. Include this AA, second moment. But the second moment, the calculation will be using this formula will be, the volume will be different from the original one. But anyway, for the tumor, if we only consider that's a two character combination, that will be 24 dimension. Okay, another advantage is this one, as I said, that's okay, that's a directional. And another one, that's okay, this one, the asymmetric, we can extend it to a very high, order, expanded. Like 3 more, 4 more, 5, until you know which, high you want. Now, let's give example, this one, okay?
So let me ask you something. What about triple combinations?
Yeah, that's what we'll introduce later. Streamer, that we call streamer, 4 more.
Okay, but yeah. Do you keep, but then your dimension vector keeps increasing length?
Yes, we'll see. Okay. We'll see how long, okay. Okay. Now see, okay, for example, if we calculate the tumor, like we have this DNA sequence, that's a 10 lengths. Then according to the formula, we will see, okay, if you count 3A appears here, 2C, and 3G, and 2T. Then that's a mean for dimension. Then calculate a symmetric covariance. That's okay, the calculator you will see, okay, AC will be, according to the formula, will be only happens in this first position, second position. So the I is the first position, second position. If you calculate this one, that will be this volume. And for the CA, we just give you example. That's a CA. If you do the same thing, that's the volume is different from this one. So that's why we study the the asymmetric. And in here, the GT here, you see that happens twice. Okay, GT here. So that will be at a 4 position, 5 position, 7 position, 8 position. If you sum this one, we will get this one. So anyway, according to this formula, we can easily calculate 24 dimension. So that's for this. You can think of what's your advantage. You have a 10 dimension, you get the 24 dimension, your increase, right? But that's not the point. We know that's okay. The DNA sequence for this simple example, that's only 10 lengths. But you can think of normally the DNA sequence is very, very long. But we all embedded into this 24 dimension.
How long you're talking about? 1,000 million?
Yeah, that's depending on which, that's like the COVID-19, 30,000. For other smaller one.
So your coming from space with several thousand dimensions to 24 dimensions.
Yeah.
How do you argue that these capture the main information of that sequence?
Yeah, that's from another paper. They study the conventional or another, principles. If you get the very, very long, high order, mathematically, you can think of that approximate your original, the character features.
Well, unless they have the same order, how can I argue that?
Yes, that's not exactly proved.
No, but actually there's another issue also. If your sequence is 30,000 characters long, then your first few coordinates are basically telling you what's the chance of A appearing in the first and the second and the third all the way up to 30,000. So that's a 30,000 dimensional vector.
Mm-hmm.
And then you're doing two combinations, A and C, A and G, that's
Yeah.
another. And then you're doing 3, and that's another. So your vectors are much larger than 30,000 dimensional vectors.
No.
Why not?
No, we only count the statistically, like the 4 dimension as the numbers.
I know, but for instance, the second number, which is
Yeah,
a 2.
the second the
Isn't-
covariance. Okay, the covariance for the the tumor
No,
only
in this
16.
sequence down here, the first number is 3.
Yeah.
The second is a 2.
Yeah.
Isn't 2 the number of times character C appeared in the sequence?
Yeah, that's
Okay.
C. Here.
So then you need to have a number of times character. Okay, so that's actually the few is very, very short. There's only 4 numbers, right? But then when you have two word combinations, 3 word combinations, 4 word combinations, it keeps going, right?
No.
No.
No,
but
no,
I mean,
yeah. If you think that's a 2 combination, that's the only possibility as a 4 square. So that's a 16. So that's why. Okay, let me tell you this one later. Okay, that's a high dimension. Let's give you example. This one. Okay, and for tumor. Okay, the first 4 it's a count. Okay, ACGT count. The next 4 is the mean. Right? Then that comes together with a tumor, that's a 24 dimension. And for 3 more, we have another 64. That's a 4 to the power of 3, because that's all the combinations.
I see.
ACT, ACG, ATC, all the combinations. That's a 64.
So you don't care where they come.
No,
you just care how many times.
Yeah. We
That's
must,
okay.
We don't care. Actually, we have some, from the formula, we embedding, the numbers, and also we embedding the position. Actually, in the formula, if you study that very carefully, you see we have that position. That's like the transformer. Transformer, they have the position embedding. We applied that idea into this formula. Yeah.
Then it's okay.
Yeah,
that's fine.
That means, if you have a particular sequence like ACA, that's mostly happened at the end of this DNA sequence. Then you calculate the volume will be quite different if that happens in the first sequence, first part of the sequence.
I see. But if your ground truth is just bunch of genetic sequences of people and you don't know ACA comes at the end, how do you find out?
Good question.
So the doctor tells you ACA comes at the end, then I understand. Then you wouldn't care about that.
Yeah,
but
we studied this one that's okay from the non-DNA sequence, right? The COVID-19, then something, those ones. Then later on, we based that on training and prediction. Then we do some, interesting topic, but I will not cover today. Okay. That's mutation.
For now, assuming you know where the anomalies are. Okay.
Yeah, the mutation, insertion, like, okay, that's a predicting part.
Okay.
Yeah. So here we have that like this one. A former we studied that will be position as a dimension will be 3, 4, 4 dimension. And right now we studied the longest one as a fiber. That's 1,368 dimension. And that's this volume is just how the data, the numerical data. And here we gave this 4 different DNA sequence. So you can see that okay, if you have a different sequence, actually we have a different numerical model. That's the idea. So now we can see, okay, we have a method. Now what we do, with this AI combination, how we apply it to the bioinformation, right? So we just gave you, we just listed several, that's topics we studied. But today, we only show you, okay, the first and the second one. So the first one, let's see what's the definition, the proper definition. Like the DNA sequence, we know the standard, standard base is ACGT. But, from the lab or whatever, if they determine that, okay, in this position it's A, so that's fixed. That's a certain. This position is, A, this position is C or whatever. But there are some no standard base code. That means, okay, in the lab test or whatever they use, okay, in this position, haven't determined what's the exactly it's A or C. Like this one, A or G, I give that's R in this position. Indicate, okay, in this position, I know that's A or G, but I'm not sure which one it is, right? So they give you those one that's R, Y, S, W, those one, that's we call that's not standard base. If N, it's a special one, that means, okay, can be any of these 4 correct. So we see that, actually we see that, okay, so that's all study goal. We just use our, that's a method, natural vector method. We solve the masking problem. That means, okay, in a sequence, if we mask it, we suppose we know that, but we try to detect that, predict it. So we try to solve this one. Then we, that's okay. We have the natural vectors. So we have a developer, learning network. Then we try to, train this model and predicted that's ambiguous, not standard base code. That means, okay, for example, here, that's protein, the COVID-19, the protein. We find, okay, in this, long sequence, suddenly, okay, there's R. That means, okay, R here is A or G, not determined.
Not determined is 50-50.
No, maybe 50, maybe not.
You don't have information.
No information. They just tell you, okay, in this position, it's R. That can be A or can be G, but maybe in this sequence, that's A, but in another piece of sequence, that will be G.
But it's not like a statistically 50% chance.
No.
It's not zero.
No, nothing. They just, okay, give you this information. So we try to determine, okay, for this one, if we trained this one, okay, then we determine these are in this, sequence, it's A or G. We give you this one. Like, that means, okay, we try to predict it. If you are not very sure, we just give you, predicted it's A or G. We are certain at a very high, confidence. That's all,
So if you have sequences where some of these sequences in the position of that R have A or G, then of course you can calculate it statistically and make a prediction. If all of your sequences have R in there, then there should be some other criteria which tells you there should be an A or G there. What is it?
Yeah, that's another way.
So what is it?
Yeah.
is it what?
Yeah, you still don't know.
I still don't know.
Yeah,
but
you
then
still
how
don't
do
know.
you predict what should you put there?
Let's see, what we find. That's very interesting. Okay, at a different, level, different, position, we predicted the different, character.
I see.
Yeah, and also if you train one set, data set, if you predict another one, the result will be wrong. You must at the same, data set. That because the data set, if you train, that gets the features, characters of this, data set. Then you can only predict this one. Let's say, okay, what we did, okay. Suppose we have that's a protein, that's alpha. That's a COVID-19, we extract only the protein part of those one. That's a number of records. First, we did as okay from this one because that contains no standard base. We filter out from this data set, right? Then we split this one records because that's very, very long. We split that one only 32 lengths segment because we try to use enabling that's 32 that training the data. So we're splitting this one into the older possibility 32 lengths. Then we remove, because after the split 32, there'll be duplicate. We remove the duplicate. Then we mask those one. Mask those one, we only at the position 16, 17. Like here we use this splitting window concept. That means original one, that's original one, 32, because 32 we have the 15 here, 15 here. So that's a 16, 17 position. And we, okay, suppose later we, predict this one, it's what? Then we predicted, shift a little bit, predict this position. That means we double check if on this position, two positions, we predicted as the same or not. Like for this one, if we predicted this S will be G. Okay, if on this position, 17 position, we predicted S is also G. That means, okay, we double checked on this both position, we finally predicted S as G.
If I understand your logic, you're considering the long correlations in each set and far distances. Then how do you know by splitting to 32, you are not losing those information?
Yeah, could be, but that's okay. We cannot, okay, we'll see later. That's okay. We have this 32 because we want to use limited, dimension, the floating numerical numbers. Okay, for this example, we just use this 32 because finally our, testing shows that 32 we can get a very, very high, confidence number. We use a probabilistic, that's determine those one. Okay, let me show you,
So they split it in a given length, let's say. They do the training and they do inference. Then they compare it with the probability distribution that they get from the ground truth. It might be that 32 is not optimal, but eventually it will tell them where to split it because they can always compare it.
Yeah,
you always compare probability distribution of 16th character with the ground truth.
Yeah, normally, okay, for this problem, we find that, okay, 32, that's we use the 88, that's a 3 mer, that's enough. But for other problem, harder problem, we use a 5 mer, that's, the dimension will be 1,368. And so then we, that's training this network, and finally we can get very high, that's numbers. And I think that's okay. Okay, now let's go to this very interesting predicting, recovering part. Okay, basically, let me show you, okay, this one we can understand this one. That's original, that's a sequence. Okay, after the training, we find, okay, in the predicting part, we don't, filter out this one. So in the original, that's we use the same data set. After the training, we try to, determine what's this one. Then, okay, we first did is that, okay, replace this one with N, that's a mask. like mask, because there's a Y can be K. Anyway, we always using the N. Then using that's over that's a natural vector. We calculate this numerical data. Then after the training, we predicting this one. For this one, and we predicting this one. In this sequence, that will be T. And that's a 16 position. And in 17 position, we also predicted that's a T. Now the predicting, that's can be, probability can be very, very high. For this example, that can be, 0.99. So as a 16, we predicted this one, that's a K, will be G. At a 17, we predicted this G, this T, K will also be G. And the probability is very, very high. That means, we are certain this K in this position, in this sequence, in this position will be G. And we can see that, for example, in another sequence, in here, that's also K. But in here, we predicted that will be T. Because this K can be, G over T. That's the, if this sequence, this Y, K, appears at a different, that's positions around that one, then we, predicted will be different, correct? But we cannot sure, as you asked that question, we are not sure it's a 50% or 50. We don't know. That's totally depending on this partial sequence in which position of your long, very long sequence. That basically determine, your neighborhood. And here, as you see, that's why we use that 32, because 32 we also get very high, length. But if we studied, initially we studied not 32, we just using those, like 16. You have less information, left, right, then you get the probability will be very low. You can think of that if you only using 4 characters to predicted, and certain, not standard code, your probability will be very, very low. So that's the way we get this one. So after, study for the COVID-19, we see that, we can get very high level, that can be success rate can be 99.89. The success rate means, if we have R, we predicted it's A over G, we consider that's a success. But there are some examples that's an invalid pattern. Like this one, we gave this R, we predicted it's a T. But your R is A over G, but Y we predicted it's a T. And also the probability is very high. That explanation may be, you marked it wrong, right? In all those, testing, lab testing, you mark it wrong. That can be another probability.
How many of them are?
See here, that's only 52 fail. But the 52 failed, mostly you can, divide it by 2 because we double, So around this 48,000 records. So that's a reach as a success reach is very high. Let's I think still have a few minutes. Now let's talk about another application. That's like coding RNA, no coding RNA. That's very popular topic on the bioinformation. Now the coding RNA basically that's can be, you can think of that's just it can be translated into protein or not. It's a coding. And the no coding recently studied, many experts studied, researchers studied this area. It doesn't translate to the that's a protein, but can help or play a key role in the translation. So that's very also useful. Now we try to study this that's coding and no coding RNA. And using the same thing, that's another paper that we find recently. They say, they claim they can have this no coding RNA. They can have the prediction accuracy as high as 98 percent. This one, that's their data set. That's their accuracy here listed here. That's they study the no coding. They have 7 types. This one tRNA, Y, R, 7 type, this one. And they have this, they use this multimodal, like multiple, structures, using the transformer, did this one. Now our goal is also doing the same thing, but we try to use our, asymmetric natural vector. And we try to, let's get, better than their result. So our, in this paper, we just say, okay, we try to classify. First, we try to distinguish RNA with no coding RNA, coding RNA with no coding RNA. On that paper, they didn't do this part. And also, we do the same thing as that paper, no coding RNA. Now, the data set, okay, we use the original papers. They have a 2 data set. They have the 7 class. And we can do more. If we use the ChatGPT, we suggested, okay, another, 7 class. That's the most popular no coding RNA. So if we combine this one with that one, that's we get a 10 set. And also we give the 20 set. 20 set here, you can see that's almost cover the data set. That's RNA Central. That's a database. That's give you all the no coding RNA, very, very large. And the 20 set can be, 20,000 those one, records. Now we try to, okay, classify all those ones. See if we can, get a very high accuracy or not. Now that's our result. Okay, that's a coding, no coding. We have this, accuracy, this one. Accuracy, this one. But back to this one, back to, I think, let's see our result first. Our result, you see, for there, that paper, we use the same data set. We almost, get the 1%, 100%, correct. That's using the 5-mer. 5-mer, that's okay, 1,368 dimension. If we try to reduce that to 24-mer, 24 dimension, we also get, 0.99. Still, that's good than their original report, right? So that's our, but back to here, why we have that, very high level, that's accuracy. Because we have that convex Hall analysis of their 2 data sets. Now the convex Hall, like you see, you try to classify something. Basically, if you try to, that's try the, visualize those one, that's one class here, one class here. If you, projection into the 2-dimensional, they'll be separate. But if no, no to the 2-dimensional projection, the general, that's study this one, that's a convex Hall. That's basically you have a class here, you need to, study the intersection. If these are 2 class, intersection or not. From our mathematician, we are very familiar, right? If we have a different, 7 class, we have this 7 class. If you 2 class, think of the data set. Okay, that's 2, 2, so that's all together at this one, 21 possible. And we say, okay, there's no intersection in their data set. If your data set, there's no intersection, that means, okay, your machine learning or neural network, after training, you should get this result, right? Because your data set, see all those data sets as a separate. No intersection with each other. So whatever you try to learn the neural network or machine learning, you should get the best optimal solution as a 100%. So that's why, that we get this one, because they are all, intersection pair as 0. But if we reduce this one to 4 more, to only 4 characters, there's some, intersection. But the intersection, okay, it doesn't mean, okay, intersection. 1 point in the middle, it's also intersection. If you have a few, that's a point in the 2 set intersection, that's still, intersection, right? So that doesn't tell you too much. That only tells you, okay, that's the intersection. But we give this one that just tell you, okay, we reduce this one, there'll be intersection. Then our machine learning, we'll see, okay, the accuracy will be reduced a little bit, but not too much. So that's why, we give this, pictures, that's a dimension. And here we see, okay, even for the 24, we have this good result. And of course, we have the 10 label. If we increase this one, not 7 label, but to 10 label, we use the random, forest. We can also get this 2,9. Okay, this 2,9. That's a 10 label. If we increase this one to 20 label, our result is also very good. Okay, so I think that we stop here. Thank you.
All right, questions?
Yeah, maybe more questions.
So the fact that you can predict that the correct correct character for each seed, showing that it doesn't carry much information. Am I correct? Means that the coding of information in this sequence is not efficient at all. In a way that if you remove one of them, you can, with a very high accuracy, say which one was removed. Means that that one didn't carry much information. Is it fair to say so?
No.
I don't fully.
He has an anomaly. So he says, I am able to predict what that character should be there based on higher correlation.
Sure. But it means that there was not much information there. Otherwise, all of them should come
with plenty of information.
No. I mean, if that one comes with very high accuracy predictable, it means that there was not much information. If you know what is...
understand the logic. I mean, based on correlations, he can make a good prediction of what that
means that there is not much information. If you can't tell what comes, then...
No, the idea that's from my understanding in the bioinformation, they do some lab testing. They testing this one. They have a overloop testing, overlap testing, but finally they couldn't determine, okay, in that position what's the correct it should be. But they know, okay, there's a position in there, but they just don't certain what correct. Then, okay, because that's in a very big, that's a data set, most of them they can determine, right? And for this, like this alpha, delta, beta, those, COVID-19, each, family, they have some characteristic. If we remove that one, you can think, okay, if you don't remove, that means, okay, something somewhere they already determined, right? So maybe, okay, in another place, they determined all the positions they determined, we training those ones, then we apply those rules to the undetermined one part. Then we try to predict it. Maybe that in that unpredicted, they maybe lose something or not. That's I'm not quite sure. Maybe they just couldn't for the lab environment in this position because they do the testing, they cost some money. They couldn't try multiple times. If they try multiple times, maybe they already determined. But overall, that's just give you, okay, if you have limited that's money or device or environment. If you give me a reasonable, stage, we can help you. Okay, this in this position, like the K is A or G, right? We determine this one. Then you do, you are not trusted. Then you can focus on this part. Do okay, try see if it's comes with align with our result. That gives the idea. On this position, you try this method. Yeah.
More questions? So one thing I'm wondering, so let's say in the place where you don't know that character, okay? So your idea is that we mask it and we want the machine to guess what that character is. I pick a window and I sweep this window on my code and I look at other configurations and I just do the thing that transformer does. I have this sequence of characters, predict for me the next character, whatever it says based on the remaining part of the sequence with a high probability, then I can guess what is going to be here.
Yeah.
My question for you, how do you, I mean, why don't you just pick the the whole sequence. You don't need to cut it for the 32, right? I mean, if you cut it for 32, then you'd have to do multiple things, because this window of length 32 need to also move horizontally on these sequences.
Yeah, that's no way to do that. That's out of memory already. Before do that,
I'm saying
even try
pick,
the
pick it largest.
No, before
What's
we
the
try that,
problem?
we try the the RNN, that's like LSTM or GRU or even transformer. One that's a drawbacks, that's very slow, very slow. And another one that's even for the transformer, long sequence. If you study the transformer, they will study the sequence. The traditional way to do that is a sequence to sequence, right? You predict this one, but the code they will cut down. And the cut down, if you study that one, okay, they always 256 or another a little high level 1024. They must cut at some point. There's no way you can handle that's like over 10,000. No.
I see.
Check your result is stable if you change the length. Instead of 32, if you start with 33, you get.
I think if you start with 33, it becomes more accurate.
Yeah, I started 32. I started 64. 33.
He's trying to say if your window increases size, you will get better. Better
Yeah, could be, could be.
Obviously.
Yeah.
No.
Yeah.
So two quick questions. One is why do you care about the symmetry? Somebody says that they come symmetrically.
No. Initially, they proposed this one. That's several years ago. I think that's 3-4 years ago. They think of that's a correlation, right?
Yeah, but why
that's
do you
relation.
Why do you care about this asymmetry?
Yeah, that's because the direction. Okay,
so
the sequence. Okay, the sequence that's there. They must follow each one by each one.
I see. So
but
you
the
want
follow
to
that's a direction.
Reduce the number of possibilities. You orient it.
Yeah.
Okay. And what do you take moment? Moment. You can say I am interested in joint probability of A and C and A and C and G, and you can do it. You don't. Why do you take moment? Somehow.
Yeah, that's Stephen original paper. They propose those moment those one. They think of that. Okay, if you give, they also study the where that appears, but that gets the highest order. Okay, that appears in which that's depending on the moment high order. That's a traditional study. That's why that's called the natural vector. That's because everything that we based on, there's some natural meaning.
They wanted to find deviation.
Yeah.
Okay, instance. Any more questions? All right, let's thank the speaker again.